So a lot of what you're going to see I took from these people who did a very nice survey of body area networks, how they operate, some of the problems. And the stuff that you're going to see is fairly recent. They're from articles that were published in 2012, which means they're about 6 months out of date. And they give us a pretty good view of what body area networks look like now, what some of their problems are. So we're going to look at the history is, how you use them, and where we're going to go with body area networks. So we have all these sensors on our body, and we have wired systems and wireless systems. And wired systems, I always thought of wired systems as being the easiest ones to deal with. So for instance, if you have a sensor over the heart, a sensor here, and a ground sensor someplace else for EKG, you hook them into a central unit, and then, of course, the signals are going to pump in synchronously when the heart pumps. So the problems you have with those systems that wired is that there are installation problems. For example, if you have multiple sensors on the body, they all have to plug into some unit. And you saw some of the pictures that Professor Lee had up of sensors that these people had cables running across their body in order to connect everything up. And that doesn't always work well. You can have a garment system like this, okay, which the wires are all entailed inside the garment, and they're all connected up. And those work well, but you have to have them worn as part of a suit. There's high cost for maintenance of these. They have wires break if they're in a suit. You can have connections that go bad, and they have to be repaired. And it also can be cumbersome. So I was thinking, also, if you have these wires going into a connector somewhere on your body, and it's not part of a suit, then you do a gesture and this thing pops out, you get it caught in your arm, and it comes off, and the sensor may come off. So there are lots of problems with wired networks, except wired networks don't have a lot of the problems that you end up with wireless networks. But if we could have wireless networks that are like wired networks in terms of their reliability, then we'd have a really good system where we could have multiple sensors all talking when they want to talk and getting reliable information. There's energy that you need for the sensor, and as the sensor gathers information. You can have a smartphone that acts as the sink where all the information would flow into. The problems that you have is with interference with other body area networks and also body shadowing. Two things that we'll talk about. Body shadowing is just quite incredible, the amount of energy that's lost in the body. So here we have a wireless network. So this is a wireless sensor network. This is not a body area network. And this would be your standard mobile system. So here you have a UAV is communicating with some ground stations. That's being connected up through an antenna system to go to a faraway location, maybe to another plane here. And you can see that here, if you need in a ground station to have more power, you just put more power in, because these things are fairly stable. They can be very heavy, and you don't have to really worry about how much power that you need in order to reach the network or to communicate with other systems. Body area networks, on the other hand, they've got to be low power, and as I was talking about before, if you have this person wearing a body area network which has a communication radius about this size, and this person over here has got a body area network of this size, these two are going to start to interfere possibly with each other. So that means as I get closer to Charlie's information is going to start to come over to my system. And my system's going to think maybe it's me and not him. And so what happens under those conditions? What happens if I start to skim off his information and then I can sell it to his insurance company or other kinds of things? So there are huge problems in terms of privacy and also in reliability when these networks start to interfere with one another. So here's a really good example that they show here. Given your arm span here is 2.5 meters from the tip of the finger to the tip of the finger, how many body area networks are you going to start to interfere with? And how much interference can you handle? And there'll be some slides towards the end that it will just, when I looked at it, it would just completely stun me. I couldn't believe that it was so, that the amount of loss, path loss in these networks were so high. So the problems that you have with body area networks is that the whole network is in motion. It's not like the sensory networks that they're sort of fixed, and you may have a sensor that's moving around, but everything else is fixed, but they're not. The base station, the station that's going to gather up the information, transmit and receive, the base station is weak. The reason the base station is so weak is because you're wearing this. Everybody remember, using your cell phone and ending up with a brain tumor? Okay? So you have the same kind of problem here, except now, what if all your sensors start to transmit? Now you're wearing 10 sensors, and they're all transmitting information. You can have interference by the base station being in contact with other networks. So there are some things you say, well, I'm maybe just passing somebody on the street. Well, maybe not. Suppose you're at home, and you're in range for long periods of time with other family members, for example, that also have body area networks. You can have nodes where you can be walking by a station that's transmitting at a certain frequency. You can be walking by your neighbor who's using his portable phone at the same frequency, which could interfere with your network as well. So there are a number of problems that have to be solved, and wearing body area networks is because of these restrictions. The restrictions of having a weak system that's going to be transmitting information is a real problem. So what are we going to measure here? So with these systems, you can have all of these things being measured. You have an artificial knee, you have pressure sensors on the foot, you have insulin injection, you have glucose measurement, you have ECG, you have motion sensors, you have EEG, you have hearing aid cochleas. You can have many sensors that are on the body and are communicating with a single base station. So the purpose, this is a protocol, the 802.15.6. This is a protocol for body area networks. And so here, they're looking for a low power, high reliability, quality of service here, so that the information gets to the nodes, and from the nodes, they get to the transmitter system. So some of the typical uses that you have for body area networks are EMG, ECG, for EEG. I mean, you can imagine someone who has a problem with intermittent epilepsy. Now, if you put electrodes on the head and you link them to your system could have software that could determine that there's a high probability that you're going to have a seizure in the next 5 minutes or so. You say, well, so what? But so what if you're driving a car, or you're walking across the street, or you're in a situation where you want to get yourself into a posture where you're not going to hurt yourself or hurt anybody else. So these are very important things. And if you have something like that, and you were to get a response saying there's a possibility of having a seizure or a heart attack or whatever, but it's not really going to happen because your network is being interfered with because someone is broadcasting on their CB radio or something. So there are all sorts of problems with reliability at this point. So these networks are 10 kilobits per second to 10 megabits per second, low power, because especially if you have implanted electrodes. They have fairly short latency of 125 milliseconds. The SARs, this is specific absorption rate. Now, the specific absorption rate is the is the absorption rate of the body tissue. So one of the problems that you have with the SAR is that the specific absorption rate is not constant. Because your heart is pumping, you have blood flowing, you're moving around, and so tissues are moving, and as a function, the amount of absorption of the energy changes as a function of time. And here, MICI refers to Medical Implant Communication Service, and it has a specific frequency that's used to communicate with implants. And the ISM is Industrial Scientific Medical Radio Bands. And these are bands that are used, these are frequencies for industrial, scientific, and medical purposes other than communications. So here we have some of the devices that we could have. And you have sensor nodes that are used to gather information on physical stimuli. You have a sensor hardware and power unit and processor and memory and transceiver. So this information here, or these pieces of hardware here, are either on the sensor, and they're certainly on the base station that you're wearing, that need to communicate. So here the actuator nodes are usually transmitting information, but they also can be gathering information. There are band networks that operate by, because they're so far away, because the receiving station is so far away from from nodes, that some nodes will pick up information from the neighboring nodes, then so daisy chain transmit that information along until it gets in range with the local unit, and then dump all the data into the local unit. So here, the personal device would gather all the information from the sensors, and then transmit the information to an external unit picked up by a nurse or a doctor, or just stored up on the cloud in order for it to make a decision on what is going to happen next. Here we have some of the information that you can see. That here we have a data rate, we have a bandwidth, number of bits of accuracy. So you can see that it goes from 16 bits here up to a megabit per second here. So the bandwidth of the sensors and the information that needs to be transmitted is very different, and it has a very, very wide range. But imagine all of this stuff transmitting information all at once. So you have your little base station that you're wearing, and it's trying to gather up all this information. So what's the bandwidth that it needs in order to gather all the information from all these sensors that may be transmitting this information simultaneously? So it becomes a very difficult problem for when you have just one sensor, no big problem. You have two sensors, you start to get 5, 10 sensors, and when they're transmitting and how much information they need to transmit, that's all very, very important. The problem is that aside from the amount of energy, you can't produce enough energy, the problem also is you have the effects of energy on the body. So here, during communications, devices produce heat. Not good. So you have sensors and the different nodes all can heat up because they're starting to use a lot of energy. Energy to compute things, energy to transmit things, energy to decode things. So everybody knows about the issue that we had many months ago about the laptop on male laptops. The Apple was heating it up, and men were becoming impotent because of the amount of heat that the laptops were producing. So now don't imagine a laptop. Imagine you have all these little sensors on you. All of a sudden they start heating up because they need to transmit information or gather information. The energy consumption needs to be minimized in order to save battery life, to prevent body damage that can occur when you have sensors heat up on you. And the power absorbed by the tissue is this SAR, the specific absorption rate that we talked about previously. So I just want to show you what the equation is for SAR. And the SAR has to do here with the conductivity, and P is the mass density of the tissue here, and this is the energy squared. So what's happening here, the mass density of the tissue and conductivity is always changing. Well, basically always changing, because what's going on in your body is always going to be changing because it's very dynamic. And they looked at the simulations of this. These are simulations of how different electromagnetic spectrum would be absorbed by the body. These were done by various institutions. And what I want to get to here is the amount of energy that's lost. You can see this here is about 45 decibels, and up here is about 140. Let me explain to you what a decibel is, because those who don't know. The formula for a decibel is 20 times the log of base 10 of gain. So if you have a gain of 1, which means your input signal and your output signal are exactly the same, you have dB of 0. If you have a gain of 10, then you have a dB of 20. If you have a gain of 1/10, then your dB is minus 20. If you have a gain of 100, then your dB is minus 40. If you have a gain of minus 1,000, then your dB is minus 60. So from here to here is a loss of about 100 dB. That's a lot. It's not just, change in gain of 100. No, it's not. We're talking about the log of the gain. So here is a huge change in gain that takes place with the signal. Look at this. This is about 30 dB that drops to 60 dB. So that's a gain loss of 30 dB here. When you go from the hip to the hip, so it's going from here to here. What's the loss? The loss is tremendous when you're trying to go through the body. And so the networks don't go through the body because there's too much tissue there, because we're one big bag of salty water. And so it doesn't want to do that. And so what happens is it travels along the skin. And if you put an electrode on the back and you put an electrode on the front and you think it's going to go through, it's not. It's going to have to travel around the edge, along the skin, until it gets there. And there's huge losses that take place in that path. And there are lots of reflections that take place in that path that cause interference. And what's interference? I know none of you know about this. When I was a kid, we used to have TVs that came from with rabbit ear antennas. And we'd be switching around the rabbit ear antenna, and we see Howdy Doody, and there'd be 3 Howdy Doodys on the screen. And why? Because the signal coming from the antenna that was transmitting the Howdy Doody program was not only coming to my antenna, but it was bouncing off the wall and then coming to my antenna. Bouncing off that wall and coming to my antenna, interfering with my picture of Howdy Doody. So the interference like that I just explained with television happens in these body area networks when you have multiple paths that go from the transmitter to the receiver. And those interference patterns can interfere positively and they can interfere negatively, which can cause you to lose tremendous amounts of signal.
We study many things in our laboratory, but tonight we're going to focus on sensory motor prosthetics. I'll define what that means in just a few minutes. I have a very long title, Emerging Intersections Between Neuroscience and Engineering, Brain-Computer Interfaces Meet Body Area Networks. But you could abbreviate that as we study cool stuff. We have no financial disclosures. All right. So let's begin with a bit of background. As you all know, dexterous hand movements are a defining feature of human existence. Our interactions with the physical world hinge desperately on our ability to explore and manipulate objects. Indeed, our social interactions are galvanized by touch and feeling. However, a number of conditions rob us of these quintessential human characteristics, things such as amputations, congenitally acquired lesions, degenerative conditions, of course, traumatic spinal cord injury. Now, recent decades have seen the realization of many motor BCIs. BCIs, to tie back into our introduction, that's brain, computer, interface, motor BCIs read brain signals to various degrees, and they actuate some sort of external device. That could be an anthropomorphic arm with various degrees of freedom. That's an efferent system, meaning it's one direction going from the brain to the body. And unfortunately, it only solves half of the problem. It turns out that somatosensory feedback guides all of our motor interactions. You can imagine just anticipated somatosensory feedback will inform how you'll reach out to touch various objects. You would certainly reach down to touch a spiny reptile differently than you would reach down to grab a little piece of Play-Doh that your child's dropped on the floor. Also, the rate with which we manipulate objects critically hinges on how you expect that object to behave in your hands. You would touch water differently than you would strike a piano key, for instance. So our lab is principally focused in giving back to the body that lost somatosensory communication. Just how important is somatosensory communication for motor movements? Just ask someone who's lost it. So there are clinical conditions where people lose selective somatosensation. Here was a patient of mine I saw a number of years ago. He had a lesion in the inferior parietal lobule right next to somatosensory cortex. That lesion caused seizures originating in somatosensory cortex, and we counseled him that curing his seizures and curing his lesion would involve removing that part of his brain and irrevocably change his motor function. He understood that and asked us to move forward, and we did. We mapped his operation, we performed the resection, and preserved the motor cortex and all of the cortical spinal descending tracts that you could just appreciate here in red. So he had normal function throughout the awake operation the entire time. We wanted to understand what the effect of that central deafferentation was afterwards. So we followed him clinically for, it turned out to be about a year, but this is up through a third of a year. We mapped his normal function and the affected side. In this task, it's very simple. We gave him a load sensor. It's a little device you squeeze, like imagine a Coke can that you would squeeze. And the load sensor informs a computer screen. As you squeeze the load sensor, the screen goes up and it goes down in a resource meter. The task was just to develop a target force. And once you got to the target force, the trick, the picture goes away. So you have to use just your somatosensory feedback to maintain that grip force. We call that grip force modulation. Just like you or I or this patient's normal side, you can do that task perfectly, even in the absence of vision, just using somatosensory feedback. But forever, after you remove somatosensory feedback, you destabilize the ability to even maintain a grip force. In some instances, he crushes the can. In some instances, he nearly drops it. Somatosensory feedback is critical to inform how we move. How do we solve the problem? Well, we build bi-directional brain-machine brain interface devices. We call them BMBIs. The whole circuit round trip can be visualized in this strategy slide here. We start with the brain. We work with our partners on testing and developing novel electrode arrays. In this instance, this is a flexible array that you can visualize right through to do simultaneous calcium imaging, if you're interested. You can build, as we have, and patent these little devices, the pen brain-machine brain interface that decodes neural signals, runs onboard computations, and then controls external effectors. Well, not just external effectors like a robotic arm, but also an internal effector, say for instance a paralyzed muscle, by providing electrical stimulation to that dead muscle to make it contract. Or you can control virtual arms, like this computer-controlled arm right here in our implanted patients. The more important part, as I was indicating before, is this limb, the afferent limb, the sensor-brain interface. How do we solve that problem? Say in someone who's got a spinal cord injury and has a perfectly normal motor system, I should say perfectly normal anatomy, normal muscles, fingers, joints, etc., but no communication? Well, we're working to develop implantable or wearable sensors that go underneath the finger skin. These can be battery-powered systems. They can be passive systems, as the ones we're illustrating here. They communicate wirelessly with what we call a body area network, just like you have a network at your house. This network is pinging from a little watch you would wear like an Apple Watch, or here's my Garmin watch. Could even be satellite linked if you want, but that's not this case. That information then gets sent to a novel brain stimulator that can be on the cortex, or the brainstem, or any number of locations. And that closes the loop. We innovate in all the areas in yellow. So let's start by talking about brain-machine interface and body area networks. I won't get into the details too much aside from whetting your appetite. This was our first system here. It consisted of 3 separate devices that were all linked wirelessly. Could be your iPad, your iPhone, and your iMac, for example. This is our digital signal analyzer. It can read out brain signals of any sort, local field potentials, individual units from the brain. We have sensors that you can wear on the hand. This is a flex sensor. We have stimulators that can stimulate muscles or brain tissue at various capacities. Our system has grown since generation 1. We're at generation 5 now with increased channel counts, increased capacity. This is a very fancy neural stimulator. I'm not going to bore you with the details, but you can see it makes a round trip from the brain to the machine to the body. Now, before we can implant this in a person, you want to be sure that it works in an animal, right? So we start with our little friends here. Our friend has a little backpack, just like my daughter going to school. In the backpack is the brain-machine brain interface, and it's going to stimulate this little guy's brain to give him super rat powers. In this instance, the super rat powers is a sixth sense. We're going to let him find a hidden platform that he can't see, taste, smell, or touch just by proximity. So it's a homing beacon. This is what it looks like from above when the animal is in the little water Morse maze. We've put these little green dots on the screen. The rat can't see this, but there's a submerged platform in there, and he wants to get to it. Oh, hello, little guy. There he is. All right, so we allow the rat to take a little swim. He needs a bath anyway. And we track his swim pattern. We track the time that he's in there. We track his XY coordinates. I'll just cut to the punchline. He doesn't find it, and we rescue him. Now, you turn the brain stimulator on. It's updating the brain with information on how close he is, a homing beacon to that submerged platform. Let's see what he does. Much smarter than my daughter. We also need sensors that are going to be able to go under the skin and give us some force sensation. So here we're exploring these little sensors that are designed to be skin-like. You insert right underneath the finger skin. There we are, the little sensors. You have big joints too, not just little joints. So we have an electrogoniometer that can tell us what kind of joint angles are developed across big joints like elbows and knees. We have novel brain stimulators and novel encoding mechanisms. There's a lot of busy stuff going on right here, but suffice to say that we're the first to show that you can have a chronic brainstem implant in animals for up to a year, essentially, and it's safe. That opens a door for us to take it to clinical trials in people eventually. We have novel math, and we try to map this multidimensional sensor space of lots of different fingers, lots of sensory modalities, temporal dynamics, and so on, into a low-dimensional space, which is brain stimulation. You can only deliver current and individual little pulses. As I mentioned, we collaborate with many colleagues to develop flexible and dissolvable electronics. This is an electronics array here. Here's a small version, here's a big version that you implant in the brain, and over time it dissolves away. So you may not want a device that lasts forever. Maybe you just have to rehab with the device for a couple weeks. We can also anticipate movements before you even do it. And the way that we do that is by decoding brain signals in patients that we're implanting for other reasons, like patients with epilepsy, who have a large grid implanted in the brain so we can find where their seizures are hiding. Well, while they're in the hospital getting their seizures mapped, we ask them to do some fun tasks, and John Burke has been great with this.
But why?